Thank you for the introduction. I'm going to present my thesis that is about the design and testing of whole thruster, and that also includes the use of simulations to study the behavior of the thruster. My thesis is supervised by Pablo Fajardo and Eduardo Aedo. I'm going to go through the motivations for this work and what are the issues with the whole thrusters at low power currently. Then the goals of the thesis, the methods used, and some intermediate results that I obtained so far, and what I'm planning to do next. So for the motivation, you've been introduced to whole thrusters already a lot today, so I think you already know, but it is quite accepted already that it's a mature technology that is quite performant in electric propulsion. However, in the last decades, a lot of development has been done in high power, but lower power is much less known and understood. So we need to develop low power whole thrusters, in particular for what Jaume said before, that we have now huge constellations of small satellites that require small thrusters. And the issue with this is that when we downscale whole thrusters to low power, we have, well, first of all, the sizing laws are not really known. We have power losses that arise from the large surface that we have. We have erosion, as you can see on the image. We have the erosion of the poles from ion impact. We have issues with the thermal management because as the parts get smaller, it's difficult to handle the heating of the thruster, and we need to generate a stronger magnetic field in a smaller space. So all of this is difficult to design and to manufacture. Plus, at low power, we have still quite low efficiency at the moment. And another problem that arises that is a bit a side topic is the cathode. We don't have we have very few available cathodes that provide little current, and the cathode is essential to the functioning of the thruster. So one thing that has already been proposed about 20 years ago as a solution for these problems is a new design of a whole thruster, which is cylindrical. So the central pole is completely removed, as you can see on the two schematics on the right. In theory, we're supposed to have more volume to surface, a greater volume to surface ratio, reduce the power losses, and we want to, increase if possible, or at least maintain the same performance while reducing erosion, because now we have only one pole to erode. So this is, even if it was introduced 20 years ago, it's a quite recent geometry, and few prototypes exist in the world, and none of them are commercial. So there's obviously a lot of work to do on this. Something else is that we also, in EP2, we do a lot of simulations of thrusters, and people have stated before there are free parameters or there are unknowns, and we need experimental data to feed to these codes to improve them and to make the modeling more efficient, more realistic. And we also need data, of course, to optimize the thrusters to improve the performance. And regarding the thermionic emitters, we also need to improve our knowledge of this and the capacity of modeling them. The thesis objectives about the thruster itself, it's subdivided in several topics that I will mention later. But about the thruster itself, first of all, the idea is to understand how it operates. Understand the physics inside the physics of the plasma discharge inside of the thruster. Specifically, some behaviors like how the electrons are moving inside of the channel, as people have mentioned it before, that is studied through simulations. how and where the ions are produced and accelerated. And this is essential to improve then the thruster. Then we want to understand how to optimize the design of a thruster, improve the one that we have already, learn how to use it optimally, how to use it already from scratch, get experimental data, as I said before, and we also have to validate specifically one of the codes that was mentioned before, which is hyphen, that is used to model different types of thrusters. So in this case, we want to use the experimental data that we obtain from the test of the cylindrical Hall thruster to compare with the results of the code and match as best as we can. And then the idea from the knowledge we get from this thruster, from the tests that we do, is to go towards a lower power thruster, so around 50 watts, that could operate without a hollow cathode. So the methodology, first of all, there is a part about simulation, so using hyphen that simulates the discharge with the axisymmetric peak-freed code. The idea was first to adjust the code to the geometry, because it was used before with Helicon thruster, with the traditional annular Hall thruster, but never with this specific geometry of Hall thruster. The plan was to adapt the simulations to this thruster, and then do parametric studies to see the behavior and try to learn a bit about how changing some inputs affects the operation of the thruster. Then part of the thesis is about the design of the PhD, so it was about learning how it's made and how to design one. And for this, I also used thermal and magnetic simulations. And then testing the thruster that was designed. So performing diagnostics in the plume to try to understand if the behavior of the thruster matches what we think it does from simulation, and understand what happens. Then improve the design, and then progressively slide towards this smaller thruster by testing this thruster with a filament cathode to try to slowly get rid of the cathode and obtain a thruster that operates without the hollow cathode. So for the results, recently I spent, first of all, the prototype was designed and built already last year. It was tested at first to understand if it ignited simply, and that was done with a cathode that was very inadapted, that was oversized, and then it led to tests with the filament cathode to understand if the thruster was operating normally, if it was issues with the cathode or the thruster itself. And then recently I did a research stay abroad, and I could characterize the thruster with a cathode that was better adapted, that allowed the thruster to work properly. And so this is the test facility where I did the measurements. I installed the thruster with the cathode that you can see there. That is still a bit oversized, but it works. And I installed the probes on a system that positions them, and then I did scans of the plume properties. So I tested with 3 different probes: the Langley probe, retarding potential analyzer, and Faraday cap. And these are a selection of results that I obtained. So on the left, it's the Langley probe result, in particular electron density that we get. So it's a map of the electron density that is measured in the far plume. And this, I'm going to use it, I'm going to do, again, simulations and compare these results with hyphen results. Then in the middle, these are on the top, it's an ion energy distribution function that I obtained from RPA measurements. And on the bottom middle, it's the ion, well, the most probable ion energy in the plume. So we obtained quite good results. It seems that the thruster accelerates ions quite efficiently. So we were happy about this. And on the right, you can see Faraday cup results. So it's the on the top, the ion current density inside of the plume. And in the middle plot, it's so performance, so efficiencies of ionization and current utilization and divergence. So we obtained these results quite recently, and now the idea is to analyze these results and present them at the conference next week, and try to understand how to use the thruster at the best. During this test campaign, we observed some behaviors that could give hints about how to improve the design. For instance, the bottom picture is, it shows that there is a lot of erosion that happens at the center of the thruster. So even though we remove the central pole, we still have some erosion that happens there because of the shape of the magnetic field. And then on the right, it's just to illustrate that we observed some strange behaviors of the injection of the neutral gas. In this case, it's xenon. So the test could give us some information about all of this. Also tell us what conditions are necessary for ignition, and some information about the oscillations of the current that were mentioned before, specifically the breathing mode that we observed in this thruster. Aside from this main project of the whole thruster and then the catalyst thruster that are just an evolution of the same project, I'm also working on on emissive probes, which is related, and it's a bit multidisciplinary, let's say. So it brings knowledge about plasma diagnostics because they're used to measure properties in the plasma, in particular the plasma potential, and we use them a lot in electropropulsion. Then the idea is to study this and get experimental data to compare with simulations from the group working on ETPAC, or on the ETPAC project. And so it's related also to electrodynamic tethers that are going to use thermionic materials, which brings us to electron sources. So the same materials that are used in the hollow cathode, and potentially that we will use for the cathodeless thruster. So the approach in this project, for my part, was to do bibliographic research, understand how to use and to design emissive probes. Dimension 1, in fact 2, for the conditions that are needed for the group of ETPAC to compare to their simulation results. And then I manufactured them and tested the probes in a thruster. So this is a representation of the design. And these are the probes that were built eventually. And they were tested in the plume of electron cyclotron resonance thruster, that is the one of Marco Incingolo, that didn't present today. But, and so we measured different operating points, varying the emission level of each probe, the operating conditions of the thruster, and the location in the plume. These are some results that I obtained that still need to be processed. So on the left side, for the two different probes, on the left side you have the floating method. So basically we increase the emission level and we see the variation of the floating potential of the probe that should saturate close to the plasma potential. And on the right we have IV curves that are obtained, that are the real objective of this experiment, obtaining the IV curves to compare to simulations. and then the derivative that we're going to use to determine the local plasma potential. Again, at different emission levels. And finally, the work that I still have to do for my thesis. Well, first of all, process all the experimental data of the emissive probes and work with SADAF to compare iteratively these experimental results with simulation results. Then for the cylindrical Hall thruster, I have to work again with hyphen and do more simulations and match these simulations with the experimental data to understand how much, how we can compare them. Then there are more test campaigns that are planned with this thruster, specifically to measure the ion properties inside of the channel with the laser-induced fluorescence. And then for the cathodeless thruster, I should start testing this cylindrical Hall thruster that is existing with a filament and at low power, and then use the information learned from these tests to design a lower power Hall thruster that would operate without the gadget. And on the right, you can see an example of simulations that were already done with hyphen of the cylindrical Hall thruster. This is the plasma potential. And the bottom picture is the tests that were already done with the cylindrical Hall thruster with the 2 filament cassettes as emitters. And the achievements that I've already had during the thesis were 3 presentations at conferences, and the research stay that I did 2 months ago in France in the research lab of CNRS. And that was this test campaign. So thank you, and if you have questions, feel free to ask.